I welcome you all to the session of engine system and performance, and today we shall discuss about the measurement of volumetric efficiency. We have studied in our undergraduate internal combustion engine course that the parameter which governs the power output from the engine is essentially the mass flow rate of air or amount of air. Rather, this is one of the most important parameters. We know very well that if we can supply large amount of air to the engine cylinder, certainly large amount of fuel can be burnt and power output by the engine would be more. But we can certainly calculate theoretically amount of or mass flow rate of air to be supplied to the engine based on the displacement volume of the cylinder or cylinder design, rather number of cylinders, certainly speed and also ambient air temperature and pressure, etc. But though we can theoretically calculate mass of air to be drawn into the cylinder per cycle, the actual amount of air which will be drawn into the cylinder will be always less than that of the theoretically calculated value. The reason is there are several parts, and those parts offer resistance to the flow of air, and those parts are air cleaner, then intake valve, certainly design of the intake manifold. So, all these issues should be taken into account while the amount of air which will take part in the combustion is considered. Considering this aspect, one term which is defined, that is the volumetric efficiency, that we have studied in our undergraduate IC engine internal combustion engine course. Now, what is the definition of this particular efficiency, that is volumetric efficiency? The volumetric efficiency is the ratio of actual amount of air or actual mass of air which is drawn into the engine cylinder to the theoretically amount or theoretically calculated mass of air that should have been drawn into the cylinder during given period of time, and which is essentially based on the displacement volume of the cylinder and ambient air temperature. So, let us write let us recapitulate the mathematical form of the volumetric efficiency. So, if we write here volumetric efficiency, which is, as I said, defined as the actual mass of air drawn into the cylinder per cycle, that is, say for example during given period of time, to the ratio of, as I said you, it is defined as the ratio of actual mass of air drawn into the cylinder during given period of time to the theoretically calculated mass of air which should have been drawn in for the same time period, right. So, the ratio of these two quantities is the volumetric efficiency. Certainly, from the definition of volumetric efficiency you can understand actual mass of air or actual mass flow rate of air that will take part in the combustion is always less than the theoretically calculated value. That is why this efficiency is defined. Now, this efficiency what we could define today, as such you have studied this before, is based on cylinder displacement volume, pressure and temperature of the ambient air. So, this is what it is important to know. Now, again this efficiency is defined here valid for unsupercharged engines. What does it mean? So, if I write here, this is for unsupercharged engines. If we try to know this quantity for the supercharged engines, then we need to know what we had written over here is pressure and temperature of the ambient air, but for the supercharged engines you know very well supercharging. So, a small compressor is integrated to the system, and the purpose of that small compressor is to raise the pressure as well as it will increase the temperature. So, compression process itself. So, now if we somehow can integrate a supercharging unit to this to any engine, then that engine is called supercharged engine, and for supercharged engine we need to know the pressure and temperature of the air in the intake manifold. It is not the pressure and temperature of the ambient air, certainly pressure and temperature of the air in the intake manifold. So, that is the difference. Okay. So, now question is, volumetric efficiency should be always less than 1. Efficiency cannot be 100% that we have studied in our basic thermodynamics course. So, mathematically you know that if the displacement volume of the engine, displacement volume of a particular engine is Vs. So, you know that so basically the mass of air per cylinder, mass of air to be drawn into the cylinder per cycle is very important, right. So, this displacement volume is Vs, and then if the density of air is rho s, then theoretically calculated mass of air should be rho s into Vs. So, the amount of mass of air that should be there in the cylinder based on this calculation or theoretical calculation is rho s into Vs, that is volume into density, but then actual mass of air should be eta volumetric into rho s into Vs. Certainly eta V is less than 1, so you can understand actual mass of air should be drawn into the engine cylinder is less than the theoretically calculated value. So, now let us look at this particular term, that is volumetric efficiency. So, this is the volumetric efficiency of the engine. We are considering for this mathematical derivation or mathematical form of the volumetric efficiency. So, now the question is, if we need to know or if we need to quantify volumetric efficiency, because we are talking about engine performance. So, there are many things we have discussed until now, and those important quantities are directly related to the engine performance. In similar to those quantities, this quantity is also very important to know about the performance of the engine. Okay. So, if we need to know about this, what we need to know? We need to know the actual mass of air to be actual mass or actual amount of air or actual mass flow rate of air to be drawn into the engine cylinder during a particular cycle is very important to know. So, now there are several methods available to measure this quantity, that is actual mass of air. So, we shall discuss in today's class two different methods which are used to calculate actual mass of air, essentially to calculate volumetric efficiency of the engine. So, let us now discuss these two different methods sequentially. So, if we look at the schematic depiction, then we can see this method, this particular device which you have studied even in your undergraduate fluid mechanics course is orifice meter that we have studied. So, this is a thin plate orifice which is used to measure the actual mass flow rate of air to be drawn into the engine cylinder. Theoretically, we can calculate, and that is function of, as I said, cylinder design, displacement volume of the cylinder, speed, ambient air temperature and pressure, and all these things are important. Now, if we look at the schematic depiction, you can see essentially this thin plate orifice is integrated to the intake manifold, right. So, this is incoming air. So, if I write here, so this is incoming air. Now, this air is coming through this tube or pipe or manifold and going to the engine cylinder. In between we have this thin plate orifice, and you can see this is squared edged orifice plate. If I draw here, you know that probably you have studied, that in fluid mechanics you have studied orifice meter. So, orifice meter is these are the streamlines. So, these streamlines, that if I erase this one, or I can erase all these streamlines first, then so if we this is the orifice plate, and this is upstream of the orifice meter, and this is the downstream side of the orifice meter. Okay. Now, if we draw the streamlines, so you know that you have studied in your undergraduate fluid mechanics course that when flow is approaching this small orifice, so in the flow pathway there is a constricted passage, and the diameter of this orifice, shape of the orifice is determined based on some reason, because there are some issues, there are some criterion I should say, based on which the diameter of the orifice and also shape of the orifice is determined. Now, when the flow is approaching this orifice, then streamlines will try to you can say that they will try to converge each other, and this streamlines will they are converging, and again the trend of converging will continue until this location, if we make it CC, after that again streamline will diffuse. So, essentially to adjust to this change in flow cross sectional area, streamlines will converge, and they will keep on converging until this location, that is section CC, which is known as vena contracta. After that again streamlines will diverge. So, say for example, if we take one section 1 here, and this is CC, and if we apply mechanical energy balance equation, we can write P1 plus half rho V1 square equal to P2 plus half rho Vc square. So, that is the mechanical energy balance equation that you have studied. I am not going to repeat, right, because assuming that we are taking the same datum. Okay. Now, I will come to this point later on. So, I have drawn this schematic essentially to make you understand that orifice meter is essentially a flow measuring device, rather a steady flow measuring device, in which there is a sudden contraction in the flow area, and when streamlines are approaching this area or this orifice, they converge, and convergence continue until this particular location where minimum area is formed, and that minimum area is known as vena contracta. Okay. So, if we look at the schematic depiction that is here in the slide, so this diameter of the orifice, diameter of the tube, and also there are two pressure taps. So, all these are information about all these: diameter of the orifice, that is small d, diameter of the upstream tube, that is capital D, and positions of these two pressure taps are provided in ASME handbook. So, this is a thin plate orifice meter, and you can understand two pressure taps are there, and from these two pressure taps we can measure the pressure drop as the flow is passing through the orifice meter. Now, if we apply the mechanical energy balance equation, you can understand. So, this is, in fact, I can write this is Pc. So, if I write this is Pc, so this is Pc, right, and then we can write that Vc Vc into 1 minus V1 square by Vc square equal to 2 into P1 minus P2 divided by rho. So, by rho. So, that is the very simple expression, and I will tell you by how it is possible to measure the actual flow rate of air which will be drawn into the engine cylinder using this thin plate orifice. So, I am taking this what you have learned already in your fluid mechanics course. So, if we write one step further, then we can write Vc almost equal to under root 2 del P divided by rho, where P1 minus P2 equal to delta P, pressure drop across the orifice plate or orifice meter. Now, while writing this, we have assumed that V1 is much less than Vc, and that is quite obvious also, because if you take the, so we know that from the conservation of mass or continuity, as the flow approaching the small gap, then certainly to satisfy mass conservation velocity will increase, because assuming that the density is remaining same and incompressible fluid flow, so velocity will increase, and velocity in this particular section CC where the distance between streamlines is very small, that is the minimum cross sectional area is very high, so velocity is very high, and if we consider then flow velocity at section CC, that is in vena contracta, is much higher than upstream flow velocity. If that is the case, then we can write V1 by Vc is much less than 1, and that is why we have ignored this term and simply we are writing Vc is equal to this. Now this is the velocity that we have calculated based on the measurement of pressure between these two sections, that is using these two pressure taps. But mind it, we have written this equation, but we did not take into account the losses due to fluid friction. So if we take into account the fluid friction, so if we go to the next slide, then if we know the velocity, then mass flow rate should be velocity of the fluid into area of the this location, that is the orifice meter. So this is the mass flow rate multiplied with density. Okay. So velocity into area, that is volume flow rate, into density, that is mass flow rate. So that is again based on the pressure drop that we have measured using pressure taps. But let me tell you one thing, that we are getting Vc is calculated using this equation, and this equation does not take into account the loss due to fluid friction. So if we need to get actual mass flow rate, that is our target, so we have to multiply this quantity with some coefficient CD, and certainly this quantity should be less than 1, so that we can have actual mass flow rate. Let me repeat once again, had we not multiplied this quantity with CD, that is coefficient of discharge, we would have obtained ideal mass flow rate, which is not again correct, because the velocity Vc that we have calculated here is based on this equation, and this equation does not take into account the losses due to fluid friction. So if we need to take into account, actual pressure drop should be even higher, and then the velocity should be less, and this mass flow rate should be less, and to consider that this quantity is multiplied with CD, which is less than 1. So that is the mass flow rate. Okay. So this is that if we go back to the previous slide, so what we have done today, we have just recapitulated what we have learned in our undergraduate fluid mechanics course, essentially to know the velocity here in the orifice, because the location CC is very close to orifice. So you can approximate that the velocity Vc is the velocity of the fluid or flow velocity here in orifice plate itself. So coming back to the schematic depiction, as I said you, one important point that I should mention, if we try to have the information of actual mass flow rate of air, this device can be used provided a steady flow is ensured. So let me tell you once again, this device, that is orifice plate or orifice meter, this device can be used to measure actual mass flow rate of air with some mathematical calculation that we have discussed now only, but this device can be used provided a steady flow is ensured, because this device is a steady flow measuring device. Now if we talk about internal combustion engine, you can understand, if we talk about 4-stroke cycle engine, so out of 4 different strokes, air is drawn into the engine cylinder during intake stroke only, while remaining other 3 strokes no air is drawn into the engine cylinder. So the airflow through the orifice meter or airflow through this intake manifold is highly unsteady, periodic. So if we need to eliminate or if we need to minimize unsteadiness associated with the airflow, which will be there, which is very much pertinent to this engine system, we have to have a large tank upstream. So that is one of the important issue that you should keep in mind, that before using this device, a large tank should be integrated to this device in the upstream side, essentially to minimize or essentially to remove unsteadiness associated with the airflow, which is very much true for flow of air during intake stroke of an internal combustion engine. So now question is, the size of the tank should be very large so that unsteadiness can be minimized. It cannot be made zero, but it can be minimized. So typically a large tank is attached to this device in the upstream side, and the size of the tank should be at least 50 times the displacement volume of the engine. So if I write here just for the sake of completeness, so to minimize the unsteady flow behavior of incoming airstream, a large tank is integrated to the device in the upstream side. And so this is one, size of the tank should be 50 times the displacement volume of the engine. Okay. So this is what is important to know at this point of time. And as I said you, information about small d, that is orifice diameter of the orifice plate, capital D diameter of the tube, and positions of these two pressure traps are provided in ASME handbook. Okay. So a designer should consult with ASME handbook to design this orifice thin plate orifice meter, which will be used or which can be used to measure actual mass flow rate of air. So now let us solve a numerical problem essentially to illustrate that technique or method we have discussed in today's class. So if we solve one numerical problem that will make you more clear about this particular method, let me first read the problem statement. A 4-cylinder 4-stroke engine runs at 1400 rpm, 1400 rpm. The bore and stroke are 8 centimeter and 14 centimeter respectively. Inlet conditions are 1 bar and 305 degree Kelvin. Calculate the ideal air breathing capacity of the engine. If the pressure differential across the orifice is 12 centimeter of water and the density of water is 1000 kg per meter cube. Calculate the air velocity through the orifice. The diameter of the orifice is 3.5 centimeter and the coefficient of discharge, that is CD, that we have already discussed, is 0.65, which is less than 1. Calculate the volumetric efficiency. So there are 3 different parts. Essentially we need to calculate volumetric efficiency, but to calculate volumetric efficiency we need to know the actual velocity of air through the orifice and also the air breathing capacity of the engine. Okay. So let us solve this problem and it will help us to understand the method even more clearer way. Let us solve this problem first. So, you know that if we write here from the data given, we can calculate total displacement volume, right. So, if we write total displacement volume equal to, you know that forced cylinder. So, if we calculate the displacement volume per cylinder, then multiply that quantity with 4 will give you the total displacement volume. So, that equal to pi by 4 into bore diameter is 8 centimeter and length is 14 centimeters. So, pi by 4 into 0.8 0.08 rather, not 0.8. So, 0.08 square into 0.14. So, this is meter cube. So, this is for one cylinder, and if we multiply, so this is meter cube. So, if we multiply with 4, then it would be the total displacement volume. Okay. So, if you calculate it, the quantity that we will get is 0.002813 meter cube. So, this is the total displacement volume. Now, see this total displacement volume, as I said you, that theoretically we can have mass flow rate into the engine cylinder if it is a single cylinder engine is the displacement volume into the density of the air. So, this quantity total displacement volume is the ideal volume. So, this is the ideal volume offered by the engine. So, this is the ideal volume, theoretical volume. So, now displacement volume, that is meter cube. So, we can have volume flow rate, right. So, this is 4-stroke engine. So, 4-stroke engine means, you know, in one cycle there are 2 revolution, right. So, if it is then if we calculate number of cycles per second equal to RPM divided by 60, that is RPS, into there are 2 revolution, right. So, from the speed data we can have number of cycle per second, and that is coming as 11.66. Okay. So, knowing this, if we multiply this quantity with 11.66, we will be getting theoretically volume offered by the engine per second. So, theoretical volume of air equal to, I am writing that will be drawn into the engine. So, theoretical volume of air per second. So, if I write here per second, that is equal to 0.002813, that is meter cube, into 11.66, that is meter cube per second. So, this is 1 upon second. Okay. So, if we calculate it, you will be getting 0.0328 meter cube per second. So, that is the capacity of ideal air breathing. So, that is the ideal air breathing capacity of the engine. That is the answer of this first part of this question. So, answer to the first part of the question is 0.0328 meter cube per second, that is ideal air breathing capacity. Now, if we go to the next slide, but this is the ideal or theoretically calculated, but actual should be always less than the theoretical one, and that is why we are trying to calculate. So, you know that inlet air density we have to know from the given thermodynamic state, that is pressure is given, right, temperature is given. So, rho I equal to Pi by RTI. So, Pi is given 1 bar into 10 power 5 Pascal, right, divided by R is 287 and Ti is 305 Kelvin. So, that is coming as 1.1424 kg per meter cube. The unit is very important. So, we have calculated density of incoming air based on the thermodynamic state that is given in the problem statement, that inlet conditions are 1 bar and 305 Kelvin. Okay. So, if we go to the next slide, then what we can do next? So, you know that we have discussed in today's class, if we need to calculate actual mass flow rate of air, if we go back to the previous slide, try to understand, we need to know about this delta P, that is pressure drop across the orifice plate. And let us now again revisit the problem statement and see if any information is given for this pressure drop, for the pressure drop that we need to calculate. So, here it is given that the pressure differential across the orifice is 12 centimeter of water column and the density of water is 1000 kg per meter cube. From this we can calculate delta P, that is the pressure drop, equal to 12 centimeter, that is 12 by 100 meter into 1000 into 9.81, that is G. So, this is essentially rho G into H. So, H is 12 by 100, rho is 1000 kg per meter cube, this is 9.81. So, meter per second square, unit should be Pascal. Okay. So, it is coming as 1177.2 Pascal. So, this is the pressure drop. Knowing this, we can calculate air velocity through the orifice, that VA equal to under root 2 delta P divided by rho I. So, if we plug in the value of already, because 2 into 1177.2 divided by 1.1424. So, if you calculate, it is coming as 45.39 meter per second. So, we have calculated the velocity of air through the orifice, and that is what was asked in this question, that calculate the air velocity through the orifice. So, that we have calculated. So, answer to the second part of this question is also here, that is 45.39 meter per second. So, knowing the air velocity through the orifice, certainly we can calculate the actual mass flow rate of air. So, let us take an effort to calculate this. So, first of all, let us calculate actual volume flow rate of air, that equal to velocity of air into that this is CD into area of the orifice meter. So, this is A is area of the orifice plate, right. So, CD, if we can recall correctly, it is given 0.65, VA we have already calculated 45.39 into pi by 4, orifice diameter is given. If we go back to the problem statement, that orifice diameter is 3.5 centimeter and coefficient of discharge CD equal to 0.65. So, that we have already used, and we have calculated velocity of air is 45.39. So, this is pi by 4 into 0.035 whole square. So, if we calculate this, it is coming as 0.0283 meter cube per second. So, this is the actual volume flow rate of air. Now, if we go back to the problem statement, or in fact we have already calculated the ideal air breathing capacity, that is ideal volume flow rate of air. So, theoretically volume flow rate of air per second was 0.0328 meter per second, that we can see from here. So, this is the theoretically calculated volume flow rate of air, and we have actual volume flow rate of air. So, now we can have the volumetric efficiency eta V, that equal to 0.0283 divided by 0.0328. You can understand the actual volume flow rate of air is less than the theoretically calculated one, and if we calculate it, it is coming as 86.49%. So, I am writing in percent. Okay. So, it is 0.8649. So, 86.49%, that is the volumetric efficiency. So, this is what we wanted to calculate through this numerical problem, volumetric efficiency. Okay. So, try to understand, we have discussed about the method consistent with thin plate orifice method to calculate actual volume flow rate of air, and we have solved one numerical problem essentially to illustrate that method, and we had seen it is possible to calculate actual volume flow rate of air through the orifice, which in turn will give us the volumetric efficiency. So, now let us discuss about the second method, which is also used to measure volumetric efficiency, and that method is essentially based on the analysis of dry flue gas or hot flue gas. So, using this method also we can calculate volumetric efficiency. We will again illustrate one problem. Before going to solve that problem, let me briefly describe about this method. So, in this method we can measure volumetric efficiency provided we know the mass flow rate of fuel and also the composition of fuel. So, this is the typical layout that you can see from the schematic depiction, and this method is used to measure fuel flow rate and also the analysis of dry flue gas. So, in this schematic depiction you can see that in this engine fuel is supplied from this fuel tank, and there is a burette which is used to measure the fuel flow rate. Air is coming from this air box, and we also can measure air flow rate. Now, the exhaust gases that come out from the engine can be taken through this smoke meter and finally exhaust gas analyzer to analyze composition of fuel, composition of exhaust gases, and from that composition we can estimate volumetric efficiency. Let me solve one numerical problem to illustrate this method first. So, as I told you, this method is based on the analysis of dry flue gas or hot flue gas, but for this particular method we need to know two important quantities. One is if I write here, one is mass flow rate of fuel, number 2 is composition of the fuel. So, these two are important to know volumetric efficiency using this method, that is dry flue gas or analysis or hot flue gas analysis. So, now let me solve one. So, essentially we have to analyze hot flue gas or dry flue gas or the combustion gases or exhaust gases that come out from the engine, and based on this analysis we can quantify volumetric efficiency provided we know the mass flow rate of fuel and composition of fuel. So, let me solve one numerical problem. So, let us first read this problem statement. A single cylinder 4-stroke engine runs at 500 rpm. Its displacement volume is 6500 centimeter cube and it produces 22 bhp with a specific fuel consumption of 0.24 kg per bhp hour. So, essentially this is brake specific fuel consumption. Calculate the rate of fuel consumption by the engine. If the inlet charge density is 1.2 kg per meter cube, calculate the ideal mass of charge that can be swallowed by the engine per second. The fuel has a composition on mass basis, that is what I was talking about. We need to know fuel composition of 86% carbon and 14% hydrogen. The percentage composition on volume basis of dry flue gas or exhaust gas is 10.3% CO2, 12.4% O2 and the rest is nitrogen. Calculate the volumetric efficiency of the engine. So, let me solve this problem, because solving this problem again you will be able to understand how this particular method works to calculate or predict volumetric efficiency. So, if I solve this problem, so you know that what is given is engine produces 22 bhp brake horsepower with a specific fuel consumption of 0.24 kg per bhp hour. So, let us define what is BSFC that we have studied in our undergraduate course. Brake specific fuel consumption, the definition is mass flow rate of fuel per unit power developed. So, this is kg per hour per unit kilowatt power developed. So, that is bhp kilowatt. So, per unit kilowatt power developed, the amount of mass flow rate of fuel needed by the engine is BSFC. So, try to understand this BSFC is given that 0.24 and this bhp that is produced by the engine is 22. So, from there we can calculate mass flow rate of fuel, right. So, this from there we can write rate of fuel consumption per cycle consumption by the engine equal to 22 into 0.24 divided by 3600. If we divide this, then we can write kg per second. So, essentially this is kg per hour, and if we need to have this quantity with unit kg per second, then we have to divide by this 3600 and this is coming as 0.001466 kg per second. So, this is what we can write. Okay. So, now next we should calculate, it is written that, or it is given, if the inlet charge. Now, question is, you have studied about charge. Essentially in the context of SI engine, air fuel mixture is drawn into the engine cylinder, which is known as charge. Otherwise typically it is air, but nowadays even for the modern engines that it is not only pure air that is drawn into the engine cylinder. For multi-port fuel injection system, it is this charge, that is air fuel mixture is drawn into the engine cylinder. So, charge is nothing but air fuel mixture, or sometimes it is pure air as well. So, now we have to calculate ideal mass of charge that can be swallowed by the engine per second given the density or charge density is 1.2 kg per meter cube. So, if we go to the next slide, then we can write ideal mass of charge, mass of air or charge that can be swallowed, swallowed by the engine equal to, see it is given displacement volume is 6500 centimeter cube. So, now certainly it is 6500 centimeter cube into 10 power minus 6 meter cube into 1.2 kg per meter cube. So, meter cube and meter cube will get cancelled, essentially it would be kg, right. So, this is kg. So, if we would like to have it per second, so this quantity again per second. So, it should be 6500 into 10 power minus 6 into 1.2 into it is given, that RPM is 500, right. So, and it is 4 stroke engine. So, 500 by 60 into 2, that is number of cycle per second. So, this should be kg per second. Okay. So, if we calculate it, it is coming as 0.0325 kg per second. Okay. So, this is basically ideal mass of air that can be drawn into swallowed by the engine. So, now if we talk about dry flue gas, so dry flue gas or DFG, we consider 1 kilomole, 1 kilomole of it. So, we consider 1 kilomole of dry flue gas, and then in the problem statement it is given on the volume basis 10.3% CO2, 12.4% O2 and rest is the nitrogen. So, that means if we go to the next slide, we can write 1 kilomole of it, then we can have 0.103 kilomole of CO2, 0.124 kilomole of O2, then 1 minus 0.103 minus 0.124, that equal to, it is coming as 0.773 kilomole of N2. So, this is the analysis of dry flue gas. If we assume that, if we consider 1 kilomole of dry flue gas, from the problem statement we can write it contains 0.103 kilomole of carbon dioxide, 0.134 kilomole of oxygen and remaining is nitrogen, that is 0.773. Okay. So, now if we calculate kg of DFG, right, per kilomole of DFG. So, 1 kilomole of DFG will contain how much kg of DFG. So, that is you can understand 0.103 into 44 plus 0.124 into 32, that is molecular weight, plus 0.773 into 28. So, this and this is coming as 13.14. So, 1 kilomole of DFG contains 30.14 kg of DFG. So, that information we got it. Now, what we can see, if we go to the problem statement, in the dry flue gas carbon is present in the form of carbon dioxide, that is given. Mind it, nitrogen is given, but assuming that no NOx formation is there. So, nitrogen is there only in the N2 form itself, no NOx is formed. So, if we write, if we go to the next slide, then we can write that. So, in the DFG carbon is present in the form of CO2 and reaction is C plus O2 then CO2. So, you can understand from this that kg of carbon by kg of fuel, or I can write kilomole of DFG. So, that equal to that we can understand that 1 kilomole of CO2 is obtained from 12 gram carbon. So, here we can write 1 kilomole of CO2 is obtained from 12 kg of carbon. So, if we write kg of carbon by kg of DFG is equal to kg of carbon by kg of kilomole of DFG equal to 12 into 0.103, because we need to know how much carbon is present in 0.103 kilomole of CO2. So, this is the quantity and that is coming as 1.236. Okay. So, now let us write some chain kind of rule, that is kg of DFG by kg of fuel. Try to understand, we said that following this method we can calculate volumetric efficiency if we know about two things. One is mass flow rate of fuel and composition of fuel. So, from the composition of fuel we will see, but we know the kg of fuel, that is very important to know. So, we can write kg of DFG by kg of fuel equal to, we can write kg of DFG by kilomole of DFG into kilomole of DFG divided by kg of carbon into kg of carbon divided by kg of fuel, right. So, we can write straight away. Now, kg of DFG by kg of DFG per kilomole of DFG, that already you have calculated, that is 30.14, right. So, in 1 kilomole of DFG we have 30.14 kg of DFG. So, this is 30.14 divided by, now kg of carbon by kg of fuel. So, kg of carbon by kg of fuel, that is given from the problem statement. You know that the fuel composition has given. So, fuel composition is 86% carbon and 40% hydrogen. So, that means if we talk about 1 kg of fuel, it contains 0.86 kg of carbon, that is the fuel composition. So, try to understand, we wanted to have two things, one is mass flow rate of fuel and composition of fuel. So, composition of fuel is given, so that is 0.86. So, this quantity is 0.86. So, 0.86 already given, and kg of carbon per kilomole of DFG, that is 1 upon 1.236. So, kg of carbon by kilomole of DFG equal to 1.236. So, this quantity should be 1.236, and if we calculate, that is coming as 20.971. So, knowing this, let us now consider nitrogen mass balance. So, if we consider nitrogen mass balance, okay, and if we consider nitrogen mass balance and assume no NOx formation, okay. So, we can write kg of nitrogen, that is from air only, nitrogen will come from air by kg of fuel. Okay. So, essentially whatever nitrogen we are getting from the air, if that nitrogen is not taking part in NOx formation, so that nitrogen will be there in the DFG also. So, kg of N2 in DFG divided by kg of fuel, that we can write. So, now what we can write? So, this quantity now we can write as kg of nitrogen in DFG divided by kilomole of DFG into kilomole of DFG divided by kg of DFG into kg of DFG by kg of fuel. So, kg of fuel we need to know, right. So, you know that from the last calculation we know in kg of DFG per kg of fuel. Okay. So, that is 20.971. So, this quantity is 20.971. If we go back to the previous slide, so we have already calculated kg of DFG per kilomole of DFG, that is 30.14. So, this quantity is essentially, this is 1 upon, because it is kg of DFG by kilomole of DFG, but here we have kilomole of DFG by kg of DFG. So, it should be 1 upon 30.14. So, this is 1 upon 30.14, and this quantity if we write that 1 kilomole of DFG, how much kg of nitrogen. So, let us go back to the previous slide. We had seen that this kilomole of nitrogen is present in the dry DFG, that 1 kilomole. So, if we consider 1 kilomole of DFG, it contains 0.773 kilomole of nitrogen, then that is equal to 0.773 into, so 0.773 into 28. So, this is this quantity. So, if we plug in that the first term is 0.773 into 28, second term is 1 upon 30.14, and the last term is 20.971 that we have already calculated. So, if we do it, then essentially we are getting that kg of nitrogen, that is coming from air by kg of fuel, that equal to 15.059. Okay. So, from assume that, now we have to assume that dry air contains 76.8% nitrogen. So, that is they are in the atmospheric air, nitrogen. So, there we can have then, so from there we can say that, then we can write, so from here we can write that kg of dry air by kg of nitrogen into kg of nitrogen divided by kg of fuel, that equal to kg of dry air divided by kg of fuel. This quantity will certainly give us some clue that if we need to burn 1 kg of fuel, how much kg of dry air needed. From there we can calculate actual mass of air needed to burn that fuel, and hence we will be able to calculate volumetric efficiency. So, now this quantity that is essentially, so kg of nitrogen by kg of fuel, So, this quantity is 15.059 and this quantity is 1 upon 0.768, right. So, dry air contains 76.8% nitrogen. So, 1 kg of nitrogen, that is this quantity should be 1 upon 0.768. So, if we write the next slide, that this quantity is essentially should be equal to 119.60. So, that means if we go to the next slide, we can write that kg of dry air divided by kg of fuel, that equal to 19.60. So, fuel flow rate into the cylinder, if we go back to the previous slide. So, fuel flow rate to the cylinder is this, right, based on the bhp power developed by the engine. So, if we know the fuel flow rate, that is 0.001466, now we have this ratio. So, we can write that air flow rate equal to 19.60, so into 0.001466. Okay. So, if we write this and then we have it is coming as 0.0287. Okay. So, this is 0.0827. So, now this is basically actual air flow rate. So, this is the actual air flow rate which is needed to burn the quantity of fuel which will produce 22 bhp, right. So, then from there we can calculate volumetric efficiency eta V, that equal to actual air flow rate is 0.287 divided by that already we have calculated the ideal mass of air to be drawn into the engine cylinder is 0.0325. So, if we write here 0.0325, then we will be getting 0.8845. So, that means 88.4%. So, this is the volumetric efficiency. Okay. So, we have discussed about the measurement of volumetric efficiency, which is very important to know, because if we supply more amount of air to the engine, more amount of fuel can be burnt and the power output will be more. But there are some restrictions provided by the air cleaner, intake manifold, inlet valve, all these parts, accounting resistances from all these parts, actual airflow rate to the engine cylinder should be always less than the theoretically calculated value, and hence volumetric efficiency is defined. Now, before going to complete our today's lecture, let me tell you one thing: the factors which really affect the volumetric efficiency. So, if I write just for the sake of completeness, the factors affect the volumetric efficiency. So, just I will be writing factors affect factors that affect the volumetric efficiency. So, number one is that you can readily understand the density of the fresh charge or air after arrival in the cylinder. After arrival in the cylinder, because when the charge arrives in the cylinder, hot wall of the arrives in the cylinder, because hot wall of the cylinder will have some heat transfer from the wall into the fresh charge. It will reduce the density and essentially it will reduce the amount of air to be drawn into the engine cylinder, okay, and volumetric efficiency will drop. Number 2 is the pressure and temperature. The pressure and temperature of the exhaust product in the clearance volume. So, essentially that if the clearance volume pressure is more, so when intake stroke will occur, if the pressure inside the combustion gases which will be there in the clearance volume is more, that will create some resistance to incoming air, fresh charge. So, essentially if it is a case, then volumetric efficiency should be reduced. So, that is also very important. So, ideally pressure and temperature in the clearance volume should be such that it will not create too much hindrance for the incoming air to come in the cylinder. Then is that design of the design of the intake and exhaust manifolds, okay, and final final point is timing of the intake and exhaust valves. So, let me tell you, the design of the intake and exhaust manifolds are very important. So, intake manifold should be designed so that it will not create huge resistance to the flow of air which is going to come in. Second thing is, exhaust manifold design should be such that it will allow easy escape of combustion gases from the engine cylinder. So, those are the design criterion. Now, timing of the intake and exhaust valves is also very important, that if the intake valve opening and closing is done properly, certainly the actual mass which is needed to burn the fuel can be drawn in. Similarly, exhaust valves should open and close in time so as to allow combustion gases to escape from the engine cylinder in time, otherwise it will try to dilute the fresh charge which will be drawn into the engine cylinder during intake stroke, which in turn will reduce the volumetric efficiency. So, if we summarize our today's discussion, then we can say that we have discussed about the measurement of an important quantity, that is volumetric efficiency. We have discussed two different methods. We have solved two numerical problems to illustrate the method that we have discussed in today's class. Thereafter, we have listed down a few factors that affect the volumetric efficiency. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.